Solving general chemistry problems. Reaction kinetics. A reaction's rate can be accelerated by raising the temperature. A larger fraction of collisions have sufficient energy to overcome the activation energy barrier leading to reaction. We can also increase a reaction's rate by increasing the concentration of the reactants. This leads to more collisions per second and hence more successful collisions and a greater rate of reaction. A third approach is to introduce a new chemical species that can alter the path taken by the reaction. Remember our previous idea of a hiker climbing up to the pass between two valleys? Well, a catalyst is something like opening a tunnel through one of the mountains. We have a new path to the same valley, but it doesn't require such a high climb, and the reaction's rate can be significantly increased. In general, this happens by lowering activation energy or by constraining the molecular movement, altering the entropy change, and increasing the pre-exponential factor. We will see examples of both. Catalysis can occur homogeneously or heterogeneously. An homogeneous reaction is when the catalyst and the reactants are all in the same phase, all in the aqueous solution, for instance. Heterogeneous catalysis is when they are in different phases. The reactants may be in the gas phase, but the catalyst is a solid, and the reactants must bind to the surface of the solid catalyst to undergo reaction. Biological processes are all chemical processes, and they are usually mediated by some catalyst. In biology, these catalytic molecules are called enzymes. A catalyst takes part in a reaction, but is not consumed by the reaction. It is a reactant in an early step in the mechanism and then regenerated as a product in a subsequent step. It is not part of the overall balanced chemical equation, but it does show up in the reaction mechanism and in the rate equation. The presence of the catalyst changes the rate equation by introducing a new reactant and by changing the sequence of chemical interactions. This results in a substantial increase in the magnitude of the rate constant. A much larger rate constant leads to a much faster reaction. It is useful to recognize and highlight the difference between a catalyst and a reactive intermediate in a reaction mechanism. Let's look at a simple example to see what happens. An important component of acid rain is sulfuric acid. The gas sulfur trioxide can react with atmospheric water to form sulfuric acid, which can then dissolve in rain droplets, leading to acidification of the soil and surface water. A major contaminant in coal is sulfur. When it is burnt, the sulfur is oxidized to sulfur dioxide, which can be emitted to the atmosphere. The sulfur dioxide can react with oxygen to form sulfur trioxide. This step can be significantly accelerated by the presence of nitrogen oxides, which are formed in the high-temperature combustion of gasoline in cars. Together, the oxides of sulfur and nitrogen can react to form a rapidly forming acidic atmospheric mix that can lead to an acid rain. Let's look at the reaction to form sulfur trioxide. Uncatalyzed, sulfur dioxide and oxygen can react to form sulfur trioxide. But when nitrogen oxides are present, the following mechanism can come into play. Nitric oxide reacts with oxygen to form nitrogen trioxide. The trioxide reacts further with another NO to form two molecules of nitrogen dioxide. The dioxides of nitrogen and sulfur can react with each other, forming the trioxide of sulfur and producing back the nitric oxide. I wrote this last step for two of everything so that it balances the other steps. As we learned before, we can find reactive intermediates that are produced in an early step and then consumed in a later step. The nitrogen trioxide is clearly such a creature, and we can cancel them out. The two NO2 molecules are also reactive intermediates. We can go ahead and cancel them out too. But notice how the nitric oxide, NO, behaves differently. It is first consumed as a reactant in both steps 1 and 2, and then is produced back in the last step. NO is a catalyst in this reaction. It does cancel out from the final balanced equation. But if we consider step 1 to be the rate-limiting step, then the reaction rate is this, just involving the concentration of oxygen and nitric oxide. The sulfur species doesn't even appear. Consider this problem. The isomerization of 2-butene from its cis conformer to its trans form is catalyzed by the addition of a little bit of iodine into the mix. The uncatalyzed reaction is found to have an energy of activation of 262 kilojoules per mole. When the iodine is added, the activation barrier drops to about 115 kilojoules per mole. At 500 Kelvin, by what factor does the reaction rate increase when catalyzed by iodine. This involves rotation around the carbon-carbon double bond. It requires breaking the bond and then reforming it once the methyl group has rotated to the opposite position. The activation barrier of 262 kilojoules per mole is very large by most standards, and the cis conformer is quite stable even at elevated temperatures such as 500 Kelvin. To find the change in rate, we need to find the change in rate constant. Use the Arrhenius equation. We want to find the ratio of K catalyzed over K uncatalyzed. We expect this to be a large number as the catalyzed reaction should be much faster than the uncatalyzed one. Divide the uncatalyzed equation into the catalyzed. Note that the pre-exponential factor A cancels out. Remember that when you divide one exponential into another, it is the same as if you subtract the one exponential argument from the other. If you wanted a different mathematical approach, you could take the natural logarithm of both sides and subtract the two equations from each other, but it leads to the same answer. Gather the terms together. When you insert the numbers, remember to not mix up kilojoules and joules. Either convert the activation energy into joules, or be sure to use R with units of kilojoules per Kelvin mole. I prefer to do the first. Multiply things out and find that the catalytic rate constant is about 2 times 10 to the 15 times faster than for the uncatalyzed reaction. Now that is a tremendous increase in rate. Here's something else to remember about some catalytic processes. When an enzyme is present at low concentration, which is the common situation, its effect on the reaction rate is best described by first-order kinetics. What is the factor by which the rate of a reaction changes when the enzyme concentration is increased from 2.5 times 10 to the minus 7 molar to 5 times 10 to the minus 6 molar? Now you need to be careful with catalysis questions. They may not always be talking about its effect as a catalyst. The catalyst, the enzyme, can still show up in the rate equation just like any other reactant. In this case, we are told it shows up with first-order reaction kinetics. That simply means that its concentration is in the rate equation raised to the first power. In the question, its concentration is increased by a factor of 20, so the rate will also increase by a factor of 20. Here's another question. When a substrate is present at a very high concentration compared to the enzyme, then its effect on the reaction kinetics is best modeled as being zeroth order. By what factor does the rate of the catalyzed reaction change when the substrate concentration increases from 5 times 10 to the minus 3 molar to 5 times 10 to the minus 2 molar? Now here's another point to be made about enzymatic systems. Enzymes carry out their function because they are able to bind very specifically to only a few kinds of molecules, sometimes only one. This is a result of their very complex structure. When we have a molecule that binds to a particular enzyme, for instance the enzyme catalase binds to hydrogen peroxide to convert it to oxygen and water, then the reaction molecule is called the substrate. H2O2 is the substrate that binds to the enzyme catalase. The point here is to emphasize that you still need to remember the rest of what we have done with reaction kinetics, even when dealing with enzyme catalyzed reactions. In this case, the answer is quite straightforward. If it is zero order in substrate, then any changes in the substrate concentration will have no effect on the rate. The rate is unchanged. Here's another enzyme question. I want to bring out one more important point about their behavior. Enzymes are complex molecules with hundreds of atoms held in a very specific arrangement by weak intramolecular forces. Their very specific shape, the way the long amino acid chain folds upon itself, is critical to its specificity and reactivity. Here's a schematic graph of the way an enzyme's reactivity changes with temperature. Please explain its shape. Well, you should first notice that the initial rise in temperature is very Arrhenius-like in nature. The enzyme is increasing because of the increased energy of the reactants, the substrate and the enzyme. The substrate can poke around the enzyme more while looking for the right site to dock and undergo the chemical reaction. However, as the temperature increases further, the increased motion of the enzyme leads to the rupture of the weak bonds holding it in its specific configuration. The enzyme is said to denature. Its shape changes and it cannot perform its catalytic function, hence the rapid drop in reactivity. For a human enzyme, the peak of the curve occurs at body temperature of 37 degrees Celsius. A principal reason for our bodies to maintain a condition of homeostasis, temperature yes, but also pH and fluid balance and so forth, is so that these many reactions continue to occur at the required rate. Now here's one last catalysis question. The oxidation of thallium-1 by cerium-4 in an aqueous solution is catalyzed by the presence of some manganese ions. Here's the balanced equation, and here's a proposed reaction mechanism. Identify which species are catalysts and which are reactive intermediates. If step 1 is rate limiting, what would be the anticipated rate law? If step 1 were fast equilibrium and step 2 was rate limiting, what then would be the anticipated rate law? The key point here to remember is that reactive intermediates are produced as a product in an earlier step and then consumed as a reactant in a subsequent step. On the other hand, catalysts are just the opposite. They are consumed as a reactant in an earlier step and then generated again as a product in a subsequent step. By reviewing the reaction mechanism, you should recognize that manganese 2+ is playing the role of a catalyst. It is consumed in step 1 and produced back in step 3. By contrast, both manganese 3+ and manganese 4+ are present as reactive intermediates. Okay, so what would the rate law then be? If step 1 were rate limiting, then the overall kinetics would be according to this expression. However, if step 2 were rate limiting and the first was a rapid equilibrium, then we would write out the first expression's equilibrium constant, that we now use a capital K, and we write it to solve for the manganese 3+ concentration. Manganese 3+ is an intermediate and must not be found in the final rate expression. Now we needed that because when we write out the rate law for step 2, the manganese 3+ concentration appears, and we need to substitute it with the known reactants and constants. We substitute and obtain this expression for the final rate law. It is considerably more complex, but is still first order in the manganese 2+ concentration.